Okay, we can go ahead and get started. So today we have Dunyu Liu with us today. He got his master's and PhD in geophysics and is now the computational geoscientist here at UTIG. He's interested in addressing the complexity of earthquake dynamics with finite element models and high performance computing. His current research covers earthquake dynamic ruptures, cycles, and high frequency ground shaking with complex fault geometry as a dominant contributor. And as a computational geoscientist, Dunyu is also collaborating with UTIG researchers on geodynamic, climate, and planetary modeling. So go ahead.
Yeah, let me share my screen. That's cool. Let me go to the front. Okay. Where's the? Okay. Thank you, Aaron. It's a really great opportunity to present my work. Thank you for joining me. Thank you all for joining me today. So before I start, I want to give credit to my collaborators and Benchun Duan from Texas A&M. He was my PhD advisor, and Catherine Thara from USGS, and Doug Yu from California State University in Northridge, and they are Paleoearthquake experts. So basically this talk, I have 4 parts: the motivation, method and model, and results and discussion and summary. So yeah, maybe you know about earthquakes, but I still prepare about, several slides about the mechanical process of an earthquake. So basically you have loading, and the rocks are loaded with elastic energy, and then there is a fault that connects the 2 blocks with frictional strength, and when the stress is too high, and then the blocks breaks, and we have earthquake. It's like a really good analogy to disbanding a stick. So the challenges in earthquake research is mainly about the spatial scales, range from micrometers to thousands of kilometers. And also the temporal scale, varies from milliseconds to thousands of years. And we have a myriad of uncertainties in the process. And so maybe a good way, especially the stresses, and a good way to understand earthquake dynamics is a multidisciplinary approach. And we try to, get in as many data, as many types of data as possible. And a few years ago, paleoseismic data kind of, grabbed my attention, and I tried to tilted my modeling effort to include the paleoseismic data. And this is how I view the position of modeling, the physics-based models. And we have these scales, the temporal scales and also spatial scale. And we have a lot of observations. They stay on different, quadrants on this map. And what the physics-based model can do is to, link them together and to give us a multidisciplinary understanding of the process of earthquake. And paleoseismic data, so probably this is the only way we can, go into the past. And when we assess seismic hazard in a fault system, we basically care about 3 questions. So what, when, and where. So what is the size of the next big earthquake, and when would it hit, and where might it start and propagate? So paleoseismic data actually provide us really valuable information regarding the timings and the sizes of past earthquakes. And the paleoseismic data actually has 2 kinds of complexity. One is the recurrence. One is about the earthquake recurrence. So earthquake may not come back regularly. And the measurement of it is the coefficient of variance of earthquake recurrence. For example, you have a site, you recorded 10 earthquakes, and you can calculate the recurrence interval and calculate the COV. That's the coefficient of variation. So that's the standard deviation divided by the mean of the recurrence interval. And this value is really interesting for major strike slip fault systems, and the value is about 0.4 to 0.8. So it's actually indicating not a pure periodic behavior. There are some complexities here. And for the San Andreas fault, these values are 0.7 at two sites like Fraser Mountain and Redwood. Yeah, later we will see the figures. Another part of the complexity comes from the earthquake extent. So earthquake rupture extents vary as well. So if we have timings from dozens of sites, paleoseismic sites, then we can link them together and to infer the rupture extents with the so-called maximum rupture model. It's pretty simple, just linking the timing together. And a recent work, really good work by Sharon and Yu 2020. So they show the rupture extents are really complex for the San Andreas and the San Jacinto fault. And rupture extent matters because it is related to the earthquake size, and that's a really important factor in seismic hazard evaluation. So here we can look at the fault system we are trying to simulate and address. This is Southern California. It has a lot of earthquakes and also a lot of faults. So the right one is actually the one we want to simulate and study. And because this is a major fault here and the largest earthquake, the 1857 fault to Horn earthquake happens on this part. And okay, yeah, the figure on the right may be a little busy. And so the top panel A shows the fault geometry, and these abbreviations are paleoseismic sites, and it has different segments like the Carrizo segment, Big Bend segment, Mojave segment, and San Bernardino segment. And this is the San Andreas, and this is the San Jacinto fault. And the panel on the bottom shows the paleo seismic datings. And first we look at the historic earthquakes. So we are pretty sure where it happened. And for example, this is the 1857 Fault Tehun earthquake. And you can see it propagated from this part and past the Big Bend and all the way through the Cajon Pass. So Cajon Pass is this triple junction here, and the Big Bend is here, where the fault changed the strike dramatically. And also we have the 1812 earthquake. It basically breaks this part and also a little bit of the San Jacinto fault. And on San Jacinto fault, we have some small ruptures. Yeah, basically the latest one we know is the oldest one we know is the 1808 earthquake. But if you go further into the past, we can only rely on paleoseismic data. And it happens, Sharon and Yu, they have a pretty comprehensive, record of this area, of the paleoseismicity in this area. It's decades of work in the making. Because you dig a trench and it may take several years just to get a few data points. So for example, this location, this dot actually shows the dating, but past the datings, we have a really big uncertainties. And that's where we see these bars, this shaded area. And if we use the shaded area to connect the different dots. If we can connect them together, given the uncertainties, then we say there is an earthquake. This is the maximum rupture model. And if we go back further, we can see there are plenty complexities here in terms of both the recurrence intervals. For example, at the Elizabeth Lake site, you see the rupture don't come back regularly, and it can only go back to 600 years here. And further back, we don't have data. But basically, we can see a few types of earthquakes from this figure. For example, we see something similar to the 1857 earthquake. For example, this one, 31. We also see some similar ones like the 1812 earthquake. This one, and also this one. But we also see ruptures. For example, this one, it is kind of stopped near the Elizabeth Lake, but shorter than the Fort Hoon earthquake. And also we have this one. It's a small rupture that breaks just a part of the San Andreas Fault. And on the San Jacinto Fault, we also have plenty of complexities. So when I looked at the data, I was wondering what caused the complexity. And because I study ruptures with complex fault geometry, and I feel it is a big contributor. So why fault geometric complexity matters? So this figure is actually from Steven Vanowski's 2006 science paper, and it shows the 1968 Borrego Mountain earthquake. And you can see the rupture is pretty complex. It breaks several segments. And for example, there is a restraining step. So rupture jump over it and continue to break, and also break these small gaps and then stop somewhere here. And also there are also some big gaps. There are nearby faults, for example, the Clark Fault, but it is far away and the rupture cannot jump over. So the fault geometry is prevalence in nature and the likelihood. So from empirical data, so you gather this kind of information for many earthquakes from the world, and then you can calculate the likelihood of a rupture passing a geometric complexity as a function of the bend angle, step over width, these kind of parameters. And basically, these fault geometric complexities are conditional barriers to ruptures, and we call them earthquake gates. Like gates, sometimes it's open, sometimes it's closed. So to link, the physics-based models and to the paleoseismic observations and also other types of observations, we need the multi-cycle dynamic models, and it has 3 parts: the complex fault geometry we have talked about, and the dynamic rupture and the earthquake cycles. The reason we want earthquake cycles is because we really have big uncertainties in initial stress. If we have earthquake cycles, we can get around that issue, and then we can produce a lot of earthquakes and calculate calculate statistics and compare earthquake patterns to paleoseismic record. The reason we want dynamic ruptures is because typically it is ignored in the long-term earthquake cycle models because it operates in the milliseconds. But earthquake cycle models typically operate on years, even tens of years, thousands of years. However, the dynamic rupture produced the largest stress perturbations in the process, and the stress is basically the driving force to all the phenomena. And we have a lot of dynamic rupture model papers to show that it is very important. So we definitely want to have it. And the figure on the right shows a pretty neat theoretical study of how these multi-cycle dynamic models can can be the foundation for this work. And it was done by Dunyu and Liu, 2005. And it only simulates earthquake cycles on a simple fault with a simple geometric complexity, just a one band. And you can see here are the 4 earthquakes that are simulated. There are definitely more, but you can see they don't repeat it exactly, and they show some difference. And yeah, this is the cumulated steep distributions for all the earthquakes. And if you have these, you can calculate the statistics and then compare with the paleoseismic data. So the method, this is a numerical model, and it has 2 parts, coseismic dynamic ruptures and also interseismic stress evolution. So we use our in-house finite element code, EQDyna, to simulate the process, and it is available on the GitHub. And we also have the friction law. Friction law is really important in the dynamic rupture models because it basically governs how the stresses involved, over in the dynamic rupture. I'll just skip the equations. And another important input in the model is the fault geometry. So we have a community fault model from SCAC Southern California Earthquake Center. And it's a several decades efforts, and people just build the model better and better. And here's the movie to show. This is the 3D fault geometry, for the model we want to simulate. Basically, you can see it's vertical. And that is the reason why we can just cut maybe at a certain depth here at 3 kilometer depth, and then to use that to build our 2D model. Otherwise, if there is any change in it's not vertical, if the fault is not vertical, our 2D model will not be valid. So we have these fault segments included here. And the last input is the loading from geodetic models. That basically tells us how the strain, accumulate on the fault. So because I got the model, so we can get the strain rate tensors near the fault from geodetic model. Here I use the Smith counter and Sandwell, and then you can project the strain rate tensors on the fault, and then you can get the normal strain rate and also the shear strain rate on different locations of the fault, and then you can load the system over the long term. And I want to introduce to you 2 important angles. One is the theta. Theta is the bend angle. For example, I have at Fraser Mountain, the FM, this side, I can measure the bend angle relative to, I need to find a reference. I just choose it on the left end of the fault. It's about theta. So the fault strike change theta at Fraser Mountain. But also there's another angle, the alpha, that is from the loading. So these arrows are the loading. So, and the alpha is the angle between the maximum shear strain rate relative to the left end of the fault. So these 2 angles, alpha and theta, may be the same, and they could be different as well. The panel on the right actually shows overloading into the system, and the top panel shows the strain rate. This is not the strain rate direction, but the strain rate values. You can see on the north part of the fault here, the strain rate is really far. That means the elastic energy accumulates faster and compared to the southern part. And so the strain rate direction also changes with the fault. So this is really important. If we don't have the geodetic model, if we don't have this information from the geodetic model, we typically need to assume okay, it's uniform, but in that case, it's not good. And then we have the fault strike change. You can see this is over 40 degrees change of fault strike. That's the Big Bang. That is also why it is called Big Bang. And we also care about this quantity. Later we will discuss it. I call it effective fault geometry. So the subtraction is only give you 20 degrees. This is important to the dynamics of the system. Okay, here comes the results. So we just feed those input ingredients to the model and then run the system. And after thousands of earthquakes, we can get a lot of data, and then we try to validate the data against many types of data sets. The first thing we want to check about is the long-term slip rate. So we have, for example, 4,000 earthquakes, and each one has a slip distribution, and then we add them together, at the same location. And maybe the 4,000 earthquakes are over 1,000 years. Then, we divided the cumulative slip by the time span. Then we have the slip rate from our models. And the geologists have a pretty good sense of what is the long-term geologic slip rate for the fault system. So we want to verify the two. Otherwise, the model is invalidated. So the dashed line here, the horizontal lines here shows the maximum and the best and the minimum estimates of geologic slip rates. And the curves shows our simulation results. And you can see they fit. Actually, we ran 3 models, but basically we try to make all of them fit into this observation. And this figure shows the slip distributions for earthquakes over 6,000 years from our model A, our preferred model. And the figure here shows on the left, the y-axis is the time in terms of thousand of years. And then, for example, for this one, that means the earthquake happens around 9.2 thousand years. And then the shaded area shows the slip distribution, the size of the earthquake. And also you can see the extent of the earthquake. And this scale is for the slip amount. So the figure here I want to show you is with the geometry, loading, and multi-cycle dynamic model ready, and then we can automatically get the complexities from it. And the system show really complex behaviors. You see different rupture extents, and also, for example, here you see clusters of ruptures. And so we ran 3 models because we couldn't tell what is the frictional strength of the system is. People argue about the fault is strong or weak, but I don't think we have a concrete way to say that. So the good way is we just try to explore the parameter space. For example, sigma n here is the shear strength, normal stress on the fault. And if we times it with the Fs, that's the static friction, we get the shear strength. So apparently Fs matters a lot in the fault system. For example, we have 0.5, 0.3, and 0.7. And that will give you different strengths of the fault system. That will affect the dynamics of the system. And the 3 panels, the 3 figures on the bottom show model B, that's a weak fault and with a 0.3 Fs. And in the middle is the model A, has a moderate 0.5 Fs. And also on the right is the strong fault with 0.7 Fs. And you can see the complexity of ruptures in the system increase with the increasing static friction. So that's really, so yeah, that's the important information from this comparison. And by considering a lot of types of data sets, and we say, model A is the best. So important message from this model is we have the recurrence intervals, and we can calculate the statistics about the mean recurrence intervals and also the COV, and compare with the paleoseismic data. I pick out 3 sites: the Fraser Mountain and the Redwood and the B-dot fan, because basically the 3 sites has the most events recorded. For example, Fraser Mountain, it has 10 events over 1,200 years, and the mean recurrence intervals is about 100 years. It's pretty small, and based on this information, actually, the whole San Andreas Fault is overdue for a large one. So that's why in the next maybe 30 years, a really large earthquake, the probability of a large earthquake hit the southern San Andreas Fault is high. And this is the standard deviation of the recurrence interval. And then we can calculate the COV is 0.7. And maybe we can look at the Fraser Mountain here. Our simulated results here. And you can see our model has a larger recurrence interval and smaller COV. But at a B-dot fan site, our values are more closer to the observation here at the bottom. So this clearly shows the model still have room for improvement because we only consider one factor in the system, that's the realistic fault geometry. But other mechanical factors, we just consider them to be homogeneous. So the large ruptures in our system can be split into smaller ones, and that will help reduce these values and make the comparison better. So this part is where we want to improve. But still, I think our studies is the first one to show the COV. Other models typically couldn't generate this kind of information and make the comparison. Still, 0.4 is a good value that's in the range for the major strike-slip fault systems. And the mode of recurrence and our model, because we have thousands of earthquakes and we can calculate the histograms of recurrence intervals. For example, at Fraser Mountain, there are 2 recurrence patterns. One is about 200 years. That's the 0.2 here. Earthquake kind of tend to return every 200 years, but also 400 years. And so, right, this is from our models. Paleoseismic data still very limited. 1,500 years only give you 10 earthquakes, so it's not enough to calculate this information. And we also compare the magnitudes. So with the historic ruptures and also prehistoric ruptures. So prehistoric ruptures is the paleo earthquakes. Historic ones are after maybe 1800, year 1800, and then we have some instrument and some records, contemporary records to say, oh, we have an earthquake over there. And our model is the blue one. They show much larger earthquakes, more earthquakes, larger than magnitude 8. So, but less earthquakes, in this magnitude range from 7 to 7.5. So definitely, this is kind of related to previous underfit of the recurrence interval and the COV. So we need some mechanical factors to divide this large event into smaller ones, and then those earthquakes will fall in this range. The most important information from the studies, we have dynamic ruptures, and we can reproduce the rupture extents from paleoseismic data. So dynamic ruptures has a slip distribution and a rupture extent and magnitude and rupture time curves. So, and it's also stresses. Rupture time curves, those are the curved lines, the dashed lines here. Basically, that means, for example, let's take panel D as an example, and the dashed line shows the rupture starts at here. North of the Big Bang, fault geometry is at the bottom. And it starts to propagate bilaterally and stops somewhere near the Kohun Pass. So this rupture actually is a reproduction of the 1857 Fault Kohun earthquake. And we have 5 meters. We have 5 meters about slip. That's the shaded area. North of the Big Bang, but you can see the slip gradually taper down to 0 south of the Big Bang. So actually, this is really exciting. We can reproduce the for Kohun earthquake, and also we can reproduce the 1812 Redwood earthquake. Also, if you recall, maybe let me bring up this figure, right? So, for example, we also have ruptures. For example, this 17 plus 15, this may be a large earthquake based on the dating of paleoseismic datings. And then our model A shows such a rupture. And also this rupture 20. So the rupture kind of is stopped by the Big Bang. And this is our B-type rupture. And also we reproduce the 1857 rupture and the 1812 rupture. And also we have this one, the 1918 rupture on the San Jacinto Fault. And the G-type rupture, that's the 16, that's the orphan one, just the break part of the San Andreas Fault, and we also reproduce it. So that's really exciting, but we are also missing something on the San Jacinto, some complexities on the San Jacinto Fault. But overall, it's pretty exciting effort. Actually, it helps us answer the where question. So without dynamic ruptures, you cannot answer this question, but we kind of amazingly see all these large ruptures, they all start north of the Big Bang. And this is the important information regarding the rupture direction. Large ruptures tend to initiate north of the Big Bang in the fault system, and they tend to propagate southwards. And it is exactly what the 1857 Fault Kohun earthquake operated. And the information is important to the ground motion evaluation because based on this study by Olsen et al. 2008, so they simulate ruptures on the same fault system, but a little bit to the south. Still San Andreas Fault, but a little bit to the south. And then they simulate ruptures with 2 different directions. And they see, so the map you see here are the ground shaking amplitude. And you can see in the Los Angeles region, different rupture directions will have dramatically different shaking maps. So our study kind of direct the effort to make ground motion simulations on this part of the southern San Andreas Fault, and then to see how the ground motion is impacted by the rupture direction. So yeah, if Olsen's results hold, that means we have less risk from the fault system. So, okay, discussion, where does the heterogeneity come from? So the all the heterogeneous phenomena we see in the paleoseismic data and other data sets come from the stress heterogeneity. That's the driving force. And it has three parts: the interseismic loading, coseismic sleep on the fault, dynamically and also statically, and also the inheritance of the stresses from past earthquakes. And the diagram shows such a situation is a fault with a simple band. And you can see when we have loading here, then you would expect that the band part, the red part of the fault, will have increased the normal stress. And if you have increased normal stress, you would expect increasing shear strength. And so that's the heterogeneity, where the stress heterogeneity come from. So if you have realistic fault geometry, you will automatically expect this. And also the same thing happens for the sleep. In the region ahead of the sleep rupture front, and you will have increased stresses and decreased the stresses following the rupture front. And the stress heterogeneity is strongly related to fault geometry, geometric complexity. And this is another study I did for a different fault, but the same multi-cycle dynamic models. And at the bottom figure shows the fault geometry. And you can see there are two bands, the light blue part. And panel C shows the band angles. So large band angles actually means we would expect heterogeneities over there. And the top panel shows the shear strength. And you can see because fault geometry, fault geometric complexity is at different scales, different spatial scales, and you would expect the shear stress heterogeneity also at different scales. And so this heterogeneity is the cause of the rupture segmentation and rupture segmentation and complex COV observed. So another important thing is how to justify the stress. We don't know much about it. There are a lot of uncertainty about it, especially the absolute stress levels. We have borehole measurements and we have focal mechanisms, but basically they tell us the directions, not the absolute values. But with the earthquake cycle method, actually we can get around that issue. So putting dynamic ruptures in the earthquake cycles, stress states will evolve in a physically self-consistent way. And in that case, stress is not considered explicitly. So actually stress is just an output from the model. And then we can focus our comparison to other data sets. And I think that's a really, why the community of earthquake modeling is moving towards the earthquake cycle simulations. So I have a general principle and goal, the goal is to fit as many types of data sets with as few key mechanical factors as possible, rather than, we just have one data set like a geodetic observation and then we fit it precisely. For example, if we bring in the paleoseismic data set, then the previous comparison may not, the fit may not be good to a specific data set, but the overall quality of the model will improve dramatically. And at least the data sets that, definitely we want to consider in the earthquake study. Yeah, here is the mechanics of rupture segmentation. That means the complex rupture extent from the observation. So for geometry related stress heterogeneity is the cause. And particularly we notice about the big band area. So the empirical relation shows the restraining bands with theta over 40 degrees will terminate most ruptures. But apparently it is not the case for the big band. paleoseismic data show, oh, ruptures can go over pretty easily. So the angle of compression, the theta minus alpha, is actually why we have a lot of ruptures past the Big Bang. Because actually the loading also is rotated along the fault strike. So we kind of propose, if we want to really assess the barrier effect of restrained band, we need both information, the fault strike, the fault geometry, and also the loading information. So the future work, from the work, there are some, really important questions to answer. One is the dynamics of the 1812 and the 1857 earthquake pair. So our models reproduce the extents of the two ruptures individually. However, 1812-like ruptures are rare in our system, in our models. But the real challenge is to reproduce both the timings and the extents of the pair. So you see these two earthquakes were just separated by 44 years. So that's a really challenge. What caused that? Still unclear. But another direction, all these results point to is we need to improve the rupture segmentation near the Cajon Pass, the triple junction. So we have a really good reproduction of the rupture dynamics near the Big Bang, one major earthquake gate, but we don't have a really good reproduction of the earthquake dynamics on the San Jacinto Fault, because the fault geometry over there basically is straight in 2D. So no fault geometric complexities over there. But there are some evidence to show that 3D fault geometry could be the important contributor over there. And we hope we are still making proposals on that. Okay, so this is a summary, and I just put 2 points here. So stress heterogeneity is from interactions between the fault geometry and dynamic ruptures produce the complex rupture extents and recurrence. And so we really need to consider realistic fault geometry in the system when we simulate, when we address the complexity from observations. And the second point is the large ruptures tend to initiate north of the Big Bang and propagate southwards. So yeah, we need some ground motion simulations to see how the rupture direction, a change of rupture direction will impact the ground shakings. Okay, thank you for your attention. So I'm ready for questions.
Yeah, thanks, Dunyu. Really cool work. I'm sure it took quite a while for that all to come together. It seems like it was very complex. If you have any questions, just feel free to unmute yourself and ask, or you can post them in the chat and I'll read them out. I've got one then. You said the paleoseismic data for this area went back about 1,500 years. Is that like a pretty average sort of time to get from like trenching for paleoseismic, or is?
No, actually, I got pretty lucky for this study because, Shara and the Yu's paper came out in 2020. Really in other locations. So basically, Southern California is the only place we have such good paleoseismic record. But other places we may have one site have maybe 5,000 years data, depending on the sedimentary condition. But we don't have this many sites. So right, so it's really hard to construct such a really good picture of past dynamics in other locations.
As like a similar question. So you said that there's like the difference between paleoearthquakes and historical earthquakes due to like the measurements. So what sort of measurements, like, are they just really early seismometers, or you have like different
Yeah,
things that you can use?
my understanding is just the instrumental, we have instrumental measurements. But for the 1857 earthquake, we have pretty comprehensive contemporary records. For example, the newspapers and, to record how the building shaking and, yeah, that's kind of, that's the farthest in the past we can go. And back further, we don't have a clear dating. We have uncertainties.
Kat posted a question. How do Coulomb stress changes affect your model? Any relationship between the 1812 and 1857 static versus dynamic stresses?
Thanks, Kat. This is a really good question. Ruth Harris has a paper on this, I think, to calculate the Coulomb stress, and especially for these two earthquakes. Actually, in this model, I didn't calculate the Coulomb stress because it is not focused from this one, but also I couldn't reproduce exactly the dynamics of the two. So I couldn't get, for example, one earthquake that looks like the 1812 one, the next one just 40 years later for the, for Tehran earthquake, and calculate the Coulomb stress. Yeah, but I think that's a really good direction to check, how the Coulomb stress varies over earthquake cycles, and how they are related to the statistics, we calculate. Yeah. Thank you. I'll take a note of this question.
I have another question when you're ready.
Go ahead.
So the main thing you said you changed was the frictional component for your models.
Yes.
Is there a way that you would be able to like vary it with depth if you're trying to approximate maybe like different rock types, sort of like Kat's question with the stress heterogeneity?
Right. I think biomaterial thing is, people argue is a really important factor to consider. So do you mean to assign different frictional parameters to different type of rocks? Like
yeah, if you think, like, would that make a big difference in it?
Yeah, I think so, especially near the Cajon Pass. Actually, I think that's the second best candidate to introduce rupture segmentation over there. Right, because really the fault near the Cajon Pass is pretty straight, in our 2D model. It's just a straight line. There's no complexities over there, and but we see a lot of complexity from the observation. So, but the rock types there are really complex, and we can also try something over there. Right, I think that's also a good direction to try.
Cool. Any more questions?
Yeah, I have one.
Hi, Ethan.
Hey, so really nice talk. I'm curious about the second point. So the ruptures initiate north of the Big Bend and propagate southwards. So I would expect the ruptures to propagate in the direction where the strength of the fault is less. And then on the slide you showed with the bend in the fault, the normal force increasing on the bend should increase the strength of the fault. So I'm just curious why, maybe you covered this, but why does it propagate into the bend even though the strength is higher there?
Yeah, actually, where dynamic rupture propagate, in very early studies, people kind of infer rupture direction from the strength, even stress drop. Really for dynamic ruptures, the stress drop matters. Even though the strength is high, but the stress drop may be small, even negative. So that will impede ruptures. But based on my experience, rupture directions is, we couldn't infer rupture directions from those informations, even you gave the stress drop distribution. So the rupture, for example, it mainly, I think, first the rupture initiate at a location because the stress condition over there, break the column failure criteria. So that's why we get an initiation location, and then it really depends on how the stress drop is distributed, outside of that area. For example, when the rupture is propagating, but it hit a bump, it will be stopped. But if there's still enough energy to allow it to propagate, it will keep going. And right, I'm not sure whether that answers the question.
It does. I guess my question was that it's more complex than just the strength of the fault controlling the rupture direction.
Right, strength is not related to the rupture. It's not strongly related to the rupture. Because the stress drops could be different, even though you have high strength on the north, but you may have low stress drop in the north. So that's the thing.
Gotcha. Thanks.
Any last questions? All right. Thanks, Dunyu, again. This was
Thank you. Thank you for listening.